Good evening. I am about 30 hours late. Uh, Normally I try to do this stream around Saturday morning my time. But this weekend I had, let's see here, I had laundry, I had, laundry, and then I slept in, played video games with friends, things like that. Normally around this time of day, on this day of the week, I would be preparing for a Dungeons and Dragons game, but we canceled it this week. So instead, I'm going to be programming Game Boy. Uh, so clearly, this is obviously the highest priority in my life. Last stream we got Game Boy Color support working. Uh, and What are we gonna do this stream? This stream, I want to get the hero working. I want to make it so that you can display the hero on the screen, and then use the D-pad to move him around. And so a month and a half after beginning this project, hopefully I'll actually have an actual interactive experience. Uh, Good bound of progress to make with only a month and a half left to the competition. I've been trying to do some prep work in advance of the streams. Let me get rid of the little overlays here real quick. I've been trying to do some prep work in advance of the stream so that I can churn through them a little bit more productively and try to keep things a little bit more interesting. So there's a couple things I did to try to prepare. One of them, I mentioned last stream that I've been working on starting to experiment with playing around with Game Boy Advance programming, and I've been porting the game to the Game Boy Advance as well. And I try to race ahead of my current Game Boy progress on Game Boy Advance. And let me see if I can, let me make sure I can see my camera. All right. I tried to implement it in advance on Game Boy Advance. This is what I want to get done today, except just on the Game Boy instead of the Game Boy Advance. And so I did that, and I programmed it in the Game Boy Advance code is being written in C, and to help me out even further, I actually printed out the code. So you're probably going to see me thumbing through some paper on this just to, again, like cut down on the amount of actual thought that I have to put into this. It's more just like taking this logic and then translating it into assembly. Another thing I did is I'm going to be getting the sprites up and running. The object attribute memory code is already in place. It's some common baseline code that I have in other projects. And so that's actually been in the game this whole time. But this time around, I'm going to be creating a sprite system that runs on top of it that exists in application space. And so what I did was I took the equivalent code that existed in another Game Boy game of mine, and I just printed it out. I'm going to be thumbing through that too, using that as reference as I try to create the sprite system for this game. All right, so I think that's all of the setup. So let's all the announcements. Let's go to the main screen here. Those are the Pandocs. And pull up the code. I'm going to be focusing on Game Boy version right now. Game Boy Color, actually, the Game Boy Color code is not going to be difficult at all because I was just looking at the. I'm thinking live. So the thing about the sprite system is that you're going to have an attribute for or a byte for the attributes. And it's priority and mirroring flags, and then also the Game Boy palette number. One of the things I was thinking about before I even began this stream was that, for Game Boy Color mode, you're adding the Game Boy Color palette index. And I had it in my mind, even though I had just been reading this, that was going to be a separate byte because it's going to have to be like banking into VRAM like I have to do on the background map. That's not actually going to be the case. That's actually just going to be an attribute right here. So that's awesome. So that means that my sprite system isn't going to need to have any special code specifically for Game Boy Color. The sprite definitions in ROM are just going to be defining this byte nums, just copying over blindly, and on Game Boy it'll do the right thing, on Game Boy Color it'll do the right thing. So that will be awesome. That said, I'm still only going to focus on the Game Boy, on the regular Game Boy this stream. And so I've already got Same Boy configured over onto the regular Game Boy mode. All right. So the agenda this stream is first to actually draw the sprite. Can't display a sprite without drawing it. So let's see here. We're going to be starting up a new tile sheet. And the tile sheets, I think, were 128 by 64. And this is going to be the tile sheet that we're going to be using to represent. I have a palette in here. Not going to use that one. Let's. Oh, yeah, let's have that open. Tiles. Don't want that. Tile set. There we go. There we go. There we go. All right. In fact, let's save this as, because I just want to keep that palette around. Let's save this as the sprite set. So there's going to be a separate set of 128 tiles that I'm going to be using as the sprite tile set. And so I need a separate image for that. So let's go ahead and just erase this right now. Fill this in. Also the way, and I want to make sure that this palette stays here when I save, so I'm just going to draw these shades here. So the sprite set, the sprite tiles are going to have the player character sprites, but then it's also going to have sprite versions of the gem tiles. So what's going to happen is anytime the player shoves a gem, right now the gems are in the background map. When you shove a gem, I'm going to erase the gem from the background map, create a sprite, show the gem as a sprite, move the sprite over, animate the sprite over to the new coordinate, and then hide the sprite, write the sprite background map tiles back into the background map. But that is going to mean that I'm going to need to have these tiles in the sprite tile set, as well as the main tile set. I don't necessarily have to, like I could have them be shared. Okay, so on the Game Boy, in video memory and tile memory for tiles, you can have 384 tiles loaded. 128, depending on how you map the tiles, 128 are dedicated to the background map, 128 are dedicated to sprites, and 128 can be shared between either background map or sprites. So technically speaking, these gem tiles I could instead put into a, hold on just a moment here. Let's see here. All right. Technically speaking, like I could put these gem tiles into that shared set of tiles that are shared between the background map and sprites. But the coloring of them is going to be a little bit weird. And I'll show why very, very shortly. Because, well, I'll explain it. So on the Game Boy, so on the Game Boy, you have 4 shades of gray, right? Black, dark gray, light gray, white. And then for background maps, you get to display all 4 shades. But on sprites, you only get to show 3, and one of them is going to be, you still have 4 colors, but one of them is dedicated to transparency, and so you can only actually show 3 colors. And so you need to adjust the colors that you're displaying in the raw tile set to then map to whatever set of 3 colors you're going to be showing, and it's not exactly the same as the colors that you have in the background map, and so they're going to look a little bit different. In particular, white is always going to be the transparent color, or at least from the source data. When I load it into the tile set and then load it into sprites, the color that's white here right now will end up being transparent. Because of that, I have to change the colors of this tile and this tile, because the white would be transparent. And I'm actually going to do that right now. So what I'm going to do is go through here, and on the sprite version of these tiles, I'm going to change the light gray to dark gray and the white to, I have a fast way to do this. the light gray to the dark gray, and the white, that is, I can't do contiguous on this one, or the non-contiguous, and change the white to light gray. And then what's going to happen is when I display these sprites on screen, I'm going to be applying special palettes to them that then kind of adjust them back to the original colors, but respecting transparency. So in sprites, the white spaces here are going to be transparent, and then I'll use palette mapping to make light gray appear as white without transparency as a sprite, and dark gray to appear as light gray. All right, so I'm going to need that. And then I'm going to start with just, there's nothing else I'm going to shove here, right? Yeah, no, so none of this matters anymore. I'm going to make a sprite for the little player character here. In fact, let's copy him over. And I'm going to need to make a lot more sprites, but I'm going to start with just, actually, let's copy this one over. I'm going to make a lot more sprites, but I'm going to take care of animation later. So for now, I'm just going to make a default standing frame. And I'll do more frames and add animation later. This is the playdate tile set. So you can see it's that one. That's the playdate version. This is the sprite set for the playdate version. I'm just using it as kind of a reference and a starting point for the Game Boy version. The playdate sprites are, I think they're 24 pixels square, but this is going to be 16 pixels square. So I need to redraw it. And with the playdate version, you also saw how I have like these 2 pixel outlines around the outside edge. It's because I found on playdate, this is a Game Boy stream. Let's spend a lot of time talking about playdate. Playdate has a really high pixel density screen. It's about the size of a Game Boy screen. It's a little bit shorter, but a little bit wider, but it's very, very pixel dense. And so in order to make sprites appear the right size, they need to be bigger than they'd be on Game Boy, and it also helps to make the outlines a bit thicker for legibility's sake, because like the thing that I found is that, you know, the pixels are so small that that narrow 1 pixel outlines can look kind of like thin hairlines and can be a little bit harder to read than on something like the Game Boy. Actually, the 2 images that I have here are almost to the right scale. The Game Boy image is definitely larger as compared to the play image versus real life, but you can kind of see that, you know, the 1 pixel outlines look kind of chunkier on the Game Boy. And so on Playdate, to kind of balance the visuals out, using these 2 pixel outlines helps with legibility. All right, enough talking about Playdate. Let's draw a Game Boy sprite. So let's draw, where do I want to put the bottom of the head? Let's just start like about right there. Put feet about like that. And I'm just gonna steal Pokemon hands right now. The little circle style of hands. Let's draw. I want the eyes like that. I don't think so. No, let's put the eyes like that. Or actually, I think I could do that if I make the head just a hair wider. It's probably almost exactly a Pokemon sprite. Actually, I think. No. I want that to flare out a bit more. Maybe have it flare out even more. That's probably too much. That's just weird. I think I need to shift the head down. Actually, let's just shift all that down. So I'm talking about like Pokemon sprites. The thing about like the Pokemon sprites is that the Pokemon overall character sprites are just fantastic. More that we've like moved away from that 8-bit generation, and the more that I've kind of like looked back at 8-bit RPGs on both the Game Boy and the NES, the more that just Pokemon's overworld art is just really, really good. They got so much character out of such small sprites. And so it's like little attributes of them, like the little circular hands, are just so good. And so it's kind of hard. And so it's like, it's really tempting to just straight up steal the style when drawing my own sprites. Because it just looks so good. Should I do something like that? Did I already do that? That looks pretty good. I could do, yeah. Okay, that's starting to look kind of good. All right, so let's fill this in right now. Again, this looks weird. Like the light gray color here, I'm definitely going to map to white. And then I'm probably going to map the dark gray color here to light gray for the protagonist. But let's do that. How am I going to... Maybe something like that. Or maybe a black line. Ooh, maybe like that. Can also do that. Kind of like that. As a very Pokemon looking sprite. I think one of the big concerns I have is that even though I don't really mind that it looks like a Pokemon style sprite, just because again that art style is really, really good. I don't really want them to look exactly like the sprite that I'm worried about is the hiker sprite. Although I guess this kind of also looks a little bit like a bug catcher. The hiker sprite or the bug catcher sprite, you don't want it to be completely identical because I don't want to like actually steal those sprites. But even though it's a very good art style and I don't mind it looking like that sort of a sprite, I don't want it to be literally those sprites. Now that makes it look too narrow. Oh, right. There. I suppose maybe the hat should be wider. Maybe that. Oh. And then I could probably go in here. There. Actually, I could probably go make that look a little bit more slanted. Yeah, that's looking a little bit too wide brimmed. Let's leave it like that. Yeah. Yeah, probably gonna. Mm. No. I think that's probably going to do it. I'm probably going to end up completely filling this in. In fact, let's leave it like that. Let's leave it like that. Let's just let that be filled in to look more like clothes. That pattern might actually literally be like a Pokemon protagonist color. Let's leave it like, Does this look too much like Pokemon protagonist right now? Let's see. Pokemon Red Sprites. If it's too much like it right now, I'll have to change it. But where's the player character? Oh yeah, oh yeah, mine's gonna be different enough from that. Is that head even wider? Wow. Okay, we're fine. I'm not like completely stealing Pokemon right now. What does the bug catcher look like? Oh, is that the bug catcher? Yeah, I'm totally different from that. That's a neat idea for the hat. But yeah, I'm fine there. Actually, I really kind of like the way the hat is drooping down more. Can I steal that? As I'm worried about stealing too much, can I steal some of that? Can I make the hat do that? No, this is going to be too much, isn't it? Yeah, I like the way it's looking right now. It's a little flat, but like having some perspective tilt to it would be nice, but well, let's try it some more. Let's give it another shot. Let's see. Oh yeah, all right, yeah, yeah. It's not perfect right now, but I think that something like that is actually going to be the right direction to take. Well, thank you. I look different enough from you to be satisfied, but I'm definitely going to take that little hint from it. All right, and then what does the hiker look like? Do I look too much like the hiker? Thinking probably not, but where is the hiker? I don't know where the hiker is. Oh, is that the hiker? That's not the hiker, is it? That might actually be the hiker. Yeah, I'm totally different from that. That's fine. Yeah, all right. Okay, I'm satisfied. All right, let's tweak this hat until it looks good. That's not going to look right when I shift the palettes around. Ooh, ooh. I think this is getting there. Actually, maybe I need to pull this in just a bit. Oh, I think that's it. I think that's it. Can I? Nah. No, not that. I think this is still looking. I think this is looking about right to me. I want to add some gray in here somewhere. Oh well. I don't know. I think that's looking okay. Let's make sure I haven't accidentally destroyed the tile set just to be sure. Yep, okay, it's still there. All right. We can go ahead and leave this in here for now. It's not going to make a difference. Let's go ahead and build. So data. Ooh. Sprite set up in. Okay. In maps. Where am I including tileset.bin? Map.asm? Sure, that'll be fine. Oh, let's go to the agenda and say that this is done. Maybe might not actually be done, but because I want to see it. We're going to create sprites.asm. All right. And let's compare to, let's bring maps.asm over. Not maps.asm. In maps.inc, I don't care for. Game data.asm doesn't even exist. OEM.asm we'll talk about in a bit. Palette, map, there it is. Sprite tiles will be in wrong. Okay, so to create the sprite system, I'm going to need to initialize them first. Okay, in mapnet, hey. It's in map build when I'm loading the tiles. All right, so for now, yeah, it shouldn't matter. I should be able to just load the sprite tiles. Okay, so so the thing I'm thinking right now is that the puzzles is not the only part of the game. There's also menus that you go to before the puzzles. And they're going to have their tiles loaded. But the thing is, the menu system is probably going to be driven entirely or almost entirely by the background tile map. So it wouldn't actually hurt if I have the sprite system load the sprite tile set into the 128 tiles that are going to be dedicated to sprites, and then it just leaves it there for the whole game, because I'm never going to need that memory for anything else. So we're going to call mem copy at the end of this. So all right, and then I think it's HL as a source. Yep. And then where is address of the first 120 tiles of tile memory has tiles 0 through 7F for sprites. So that's definitely where it's going to be. Okay. Initialize systems. This needs to be global. All right. So we should do, what we should see when I reload is we should see the sprite set loaded right here. Hey, there it is. Cool. All right. Next. We need to display the sprites. But we are also going to be writing this at the same time as we're going to begin writing the code to represent the hero. So I think we're also going to create the hero assembly file right now. Let me consult some C code real quick. Yeah, okay. So we're just going to go ahead and create some hero.asm. We're going to need some, well, let's include gameboy.inc, and then section hero vars ram0. How big is my map file now that I'm including the hero tile set? We've got 3b16 left, which is 15. What is 16 kilobytes? 16.7. I'm only using about a kilobyte of space right now, and probably most of it is taken up by those tile sets. So this isn't bad at all right now. All right, and then section hero code. It's gonna be rom0. And we're gonna have a global function called hero spawn. Am I gonna want x, y? Yeah, I'm gonna want x, y there. I think I do. A hero spawn. So once per map, we're gonna load the player character. The map loader is going to call this function here, and it's going to pass in the x, y coordinates in map space. Yeah. Oh, this is gonna be fun. Okay. It's not going to return anything, but the hero at map x, map y. In other games, I might go to the effort of creating a general purpose entity system. But the thing is, this game is so limited in scope that there's hardly any entities that would even exist. So everything about the hero is just going to be like one-off code written specifically for the hero. It's going to be created separately, updated separately, drawn separately. All of its code is going to be its own. Which is going to be easy, right? Okay. So the hero vars that I'm going to want, I definitely want hero X and hero Y, and let's start with just that for now. Oh, and this is going to need to be a public routine. So can I just do db to define a single byte? Cool, I can. Another thing that's going to make this easy for me is that all the puzzle screens are going to be a single screen sized space. And so I don't have to worry about anything beyond 256 pixels. So I don't have to worry about like 16-bit formats or anything like that. I can just use a single unsigned byte to represent all these positions. So, okay, so the thing about this, the hero is going to be receiving in map X and map Y coordinates. These are going to be integral coordinates like this is one coordinate, and then this is the second coordinate, and this is a third, and this is one down. So starting from here, this is one to the right, this is one down, etc. So the maps are like 10 tiles wide. or however many they are. But when I'm working the hero, I want to be working in pixels. So I want to take this map X and map Y and turn them into a pixel space coordinate. So actually, I'm going to write a little doc here that says pixel space X coordinate. Here I'm going to define this as pixel space Y coordinate. All right, the docs came through. Okay, so nice thing about this. So here's something that's really cool. Game Boy does not have multiplication or division instructions, so you have to do it in software somehow. But there is bit shifting, which can make multiplication and division by powers of 2 affordable. And there's a very particularly awesome power of 2, which is 16. And it's easy to multiply and divide by 16 because you have the swap instruction to help you out. The swap instruction swaps the high 4 bits and the low 4 bits. And a multiplication by 16 is a bit shift left 4 times. And so if your number that you want to multiply by 16 is less than 16, I think if it's less than or equal to 15, then a swap is literally equal to multiplying it by 16. And fortunately, our map X and map Y will be less than 16. So in order to multiply map X and map Y by 16, in order to get this pixel space coordinate, we just swap the bits. So we're going to swap D and we're going to swap E. And then we're going to, can I load to N16? I can only load A to N16. So we're going to load D into A, and then load hero X, A, and then same for E. In fact, let's reorder this a bit just to make it. There. And is that all that I want for spawning right now? Yeah, we're going to do movement later. All right, and then we're going to want a public function to draw the hero. And I'm just going to stub it out for right now. I'm not actually going to implement it right now. So this is going to be public. This is already defined as public. All right. Do I have a listing here anywhere? Listing of symbols. Ooh. So I map build, generate, place initial object tiles. D equals map X, E equals map Y. Replace the graphics tiles at gameplay map X with object tiles for tile index. I think I want that. Okay, so the idea is if the tile is 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then we're dealing with the hero. And so we want to spawn the hero if we encounter tile index 9. If index first graphics tile is 0, we have a special tile. With the object tiles for tile index. C equals offset of tile index. Well, C is going to be 9. Yeah. I don't need to look up the table for that. So map place tile. Let's not write it in here. Let's write it here. Okay. So what we're going to do is, in here is C equals gameplay tile index. If the gameplay tile index is 9, then instead of calling place map tile, we're instead going to call hero spawn. All right, what registers do I need to preserve? So we're going to definitely want to keep DE around. And then I know the routine doesn't touch HL, but this is part of me wanting to experiment with the calling convention of like having a calling convention that just doesn't specify anything except arguments return values. And by convention, you have to preserve anything that you need to keep otherwise. And again, this is just me trying to figure out what do I feel about different calling conventions. This is a redundant call to push and pop, but to hold to my experimental calling convention, I'm going to call anyway. And then I think AF doesn't matter. Yeah, because I just write AF. And then what about BC? BC, I don't care about either. Okay. I don't use B for. Let's 0 into B. Oh, yeah. Okay, yeah. So I don't care. Okay, so I don't need to preserve BC. And if we did execute this and we don't need to load the map tiles, we're just going to jump to end load tile. Okay, so now if gameplay tile index equals 9, hero, call hero spawn instead of map. Call hero spawn. Otherwise, call map tile. Okay. If the gameplay tile index equals 9, which is the index, all right, so. And we happen to already have it in A. Awesome. So we're going to compare with 9. So if it's, all right. So if it is 9, then the 0 flag will be set because 9 minus 9 is 0. So if it's not 0, we want to call load tile. I think that's correct. Okay, if I got this logic backwards, I've been having a big problem with getting this conditional flag logic backwards in my expressions, but if I got it backwards, then we should not see D equals map X, E equals map Y, D equals map X. All right, so if I got this logic wrong, we should see all the map objects go away. Looks like I got it right. Just for giggles, let's actually get it wrong just to make super duper sure. Nice. Okay. So that should actually do it for the loading logic. So should be a way I can actually check this. I should be able to print out hero X and hero Y. Maybe it might be private. It might not actually be in the sim file. So let's see here. Okay. Why didn't it work? Okay. 50. So it's placing it 80 by 80. What's 80 divided by 16? So it spawned it at 5, 5. So if I look at maps.asm, I should see 9 at 5, 5. So let's check that. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. All right. Let's go to the other map. All right, and see what those values are now. 30 and 40. Okay. 30 is hex for 48, which is 3. And 40 is hex for 64, which is 4. Yeah. So 3 and 4. 0, 1, 2, 3. 0, 1, 2, 3, 4. Okay. So I think hero spawn is working correctly. When we encounter, this can go away. So now, when we encounter the hero object, we're instead calling hero spawn. We're passing it the correct arguments. It's being loaded into hero X and hero Y correctly. And otherwise, we load a map object correctly. So hero's at least positioned correctly. So now I think we can go back to the sprite logic. No, I think I'm going to declare a little bit more ROM data in the hero. Well, here, what I'm going to do is I'm going to define my my sprite struct. The way that I represent sprites in ROM. So let me consult some of my old code. Where did I define it before? Because I think I'm probably just going to use the exact same format for sprites. Here we go. Okay, put this over here. All right, please don't fall. Here, I'm gonna, excuse me. All right, there. All right. So, the struct for a sprite, and here I'm going to be a little bit particular about terminology. So what we colloquially refer to as sprites on Game Boy is referred to more as objects, which is a wonderful term because in programming, objects has come to mean something entirely different. Objects are part of object attribute memory. What we think of as sprites is usually something like a 16 by 16 pixel image with transparency, which is what we're going to be showing the hero as here. But internally, you're going to represent that by 4 objects in 2 by 2 arrangement. An object is 8 by 8 pixels. Although on the Game Boy, there's also an 8 by 16 pixel mode, which we're not going to be using. And so because of that, I'm going to be using the terminology as that. The sprite refers to a collection of objects, and the objects are more the low-level representation of what you're actually programming to Game Boy memory. The sprite is the higher-level representation of what I'm conceptually working with, which is an arrangement of objects. So the definition for a sprite is just going to be a U8 object count, and then it's going to be some objects of object count. So it's just going to be first a number indicating how many objects are in the sprite, and then it's just going to be a list of object definitions. And then an object definition, I think it's just going to end up being 2 bytes, right? No, it's 4. Okay. The previous code I did to define, I'm going to change how this works. So in my last project, I had the idea, let me just write out how the last project worked. I had SA-Y offset. I'll get into why I did that in a bit. SA-X offset, U8 tile index, and U8 attributes. Okay, so on my previous project, I let myself have some signed 8-bit integers for the offsets of each object in the sprite. And this allowed me to create complex arrangements of objects that could save tiles. So I would have things like I had a triangular sprite, which could be represented using 3 objects, one centered in the middle and then 2 kind of off in the corners. And so it made sense for me to have these 8-bit offsets I could work with. I don't need to be that flexible for this. I'm thinking uh, I'm definitely going to need like a 16 by 16 mode that uses 4 objects. And then I might also support 1 by 1 objects for maybe some particle effects and like smoke and stuff. And I really just need those 2. I don't need any others. So I think instead, what I'm going to do is, yeah, so I'm going to have a U8 for type. And then just a number of objects based on that type, and they're not going to need their offsets because there's only going to be 2 different types, and each of those types are going to have predefined arrangements that are hard coded in the system. So yeah, okay. So what's going to happen is on the type byte, I'm either going to have a 0 or a 1. If it's 0, it's going to be a 2 by 2 arrangement, and there's going to be 4 of these following it. If it's a 1, it's a 1 by 1, and there's only going to be 1 of these after it. I was thinking for a little bit, it might make sense to have the 1 by 1 be first because it seems to make intuitive sense. But for right now, I'm only going to be programming in the 2 by 2 mode. So let's just start that at 0 so I can just kind of blindly work through these things. So that's going to be my struct definition for sprites in ROM. So now let's open up a side tab. Okay, how's this going to look on the stream? I want to have a little split open. No, that's going to be legible on stream, so this is going to be fine. All right, so I'm going to go hero here. I'm going to define the sprite definition. And so what I'm going to do is I'm actually going to just literally type in the bytes for the standing idle sprite using this struct definition. So the type is going to be 0. Which then is going to be followed by 4 objects. So it's going to be $20 for the top left. It's the tile index. And then right now the attributes are going to be 0. I'm going to figure out the attributes later. It's going to be palettes. So the attributes are these bits right here. I'm never going to use priority in this game. Not going to need to flip X or Y. I might be able to save some tiles if I do that later, but it's not going to matter. I'm not going to come anywhere close to overflowing my tiles. So I'll probably just allow redundant tiles if there's mirroring. And then there's going to be palette numbers. One palette number for Game Boy and then these for Game Boy Color mode, but I'm just going to leave them as 0 for right now. Okay, so this is top left. And let's do top right, bottom left, and bottom right. Okay. So top right is 21. Then was it going to be 30 and 31? 30 and 31. Okay. So that defines an idle sprite. So that's the ROM data. All right. Next. Need this back. Where'd my C code go? Is it at the end here? Yeah. Let's set the C code over here for now. Okay. So a sprite system is going to have a routine called Sprites draw. It's going to be a public function. And then I think because of, all right, so in the previous project, I used B and C for the X and Y coordinates, but I think I have such a heavy convention for putting X and Y and D and E that I'm just going to carry through here. So D equals X equals Y, then HL equals sprite def address. Actually, let's do address of sprite definition. Doesn't return anything. Draws the sprite defined at address sprite def to shadow OAM. I should probably talk about what that is. To shadow OAM positioned at X and or, okay. So now I can call that from the hero, and that will end. That will be the end of the hero code for the map for the task for drawing the hero. So we're going to be calling sprites draw. Going to be loading HL, the ROM instance of the struct hero idle sprite. All right, so can I load the value of an N6? No, I can't. Okay. But I can here. Okay, so hero X. And that's going to go into D. Load hero Y, and that's going to go into E. So that should be the arg for sprites draw. Draws the sprite defined at address sprite definition to shadow IM position at X, Y. X at D, which we're loading there. Y at E, which we're loading there. And HL is the ROM definition. Okay. All right. And then let's make sure that we're calling all of these. Okay, so we are calling hero spawn. Next, let's call hero draw within map. Do I have a map update? I think that'll be what I want. Or should it be in main? Palette update, input update. Yeah, let's call it here. All right, and then I'm also going to have Okay, I have two more routines, I think. There's sprites and knit. It's gonna be, I think there's gonna be sprites begin frame. Yeah, sprites draw. And I don't think I have any other routines than that. Sprites draw is gonna take a little while to write, but so we're gonna have a function called sprites begin frame. So sprites begin frame. So I'm going to call it after every call to dispatch the OEM data, and sprites begin frame is going to clear out my shadow OEM, and then I'll call sprites draw repeatedly, which will draw a sprite to shadow OEM, and then at the beginning of a frame I call OEM init. So let me stub out this routine, and then I'll explain what's going on with OEM and shadow OEM. I suppose I could close this, but I'm going to be using it so heavily soon in just a minute, so I'm going to leave that open. All right, and then in main, okay. So let's talk about shadow OEM. It's like if you're an experienced Game Boy programmer, nothing I'm about to say is new. I don't know exactly what audience I'm making these streams for anyway, but if you're not a highly experienced Game Boy programmer, I'm going to explain how I'm going to go about. Oh, am I lagging? I think I was lagging for a minute there. I think it's clearing up now, though. Yeah, I've got a little green light there. All right, yeah, I think I paused for a moment there, but I should be back. So if you're not a highly experienced Game Boy programmer, let's talk about sprites. No, I am. Okay. So on the Game Boy, you have a 160 byte region of memory called object attribute memory, which is the memory that you write to in order to find all of your sprites. Since it's in video memory, you can only safely access it during a blanking period. Vertical blank is the blanking period after it finishes drawing a screen. And it's the longest contiguous blanking period in which you can safely write to video memory, including OAM. And then there's also horizontal blank, which is a very brief window of time that happens after it finishes drawing every row of pixels. And you can update video memory during HBlank, but HBlank is a little bit more complicated, well, quite a bit more complicated to work with. And in this game, I don't think I need to bother with it. So for purposes of this discussion, we're only going to be talking about vertical blank. So I can only safely update object attribute memory during vertical blank. The problem is that vertical blank is pretty brief. It only amounts to about 5% of the total CPU time available during a frame. And it's 160 bytes, and it's not a lot of time to work with all 160 bytes. What would be nice would be if instead I could write during the 95% of time during the 95% of the rest of the time, instead of the 5% of the time that's during VBlank. It would be a much larger chunk of time. So what you can do is you can instead define your own region of memory called shadow OAM, shadow object attribute memory, and you can write to that whenever you want because it's just a normal area of RAM, it's not protected. And then when vertical blank begins, what you can do is you can copy your shadow OAM to regular OAM, and then the Game Boy will read regular OAM for drawing the sprites. This is a very, very standard practice on the Game Boy. In fact, it's so standard that the Game Boy actually has a hardware feature specifically designed for it called the OAM DMA, or direct memory access. And it's a mechanism to copy a chunk of memory from RAM into OAM at very high speed, faster than you could through a regular copy. And so that's why I've already got like mostly set up. So I have a standard assembly file here that I brought in from a previous project. And it's like I'd use the same file in any Game Boy project that I have. It defines a region of memory called memory shadow OAM, which is 160 bytes that I can write to outside of VBlink. And then there's a routine called OAM DMA run, which executes the OAM DMA in order to copy the memory from shadow OAM to regular OAM. Just about every Game Boy game that you encounter is going to have basically this code. It'll be like named differently and commented differently, but it's all going to do exactly what this does. The thing is, this doesn't contain the higher level logic of this, what sprites look like. It works only on the hardware level of objects. So in the sprite system, I'm going to write code that takes these sprites and then writes objects to shadow OAM. And then I've already set up the code to run the OAM DMA. So for sprites begin frame, what I'm going to have is, so I need to have some sprite variables, and in particular, I'm going to have a section here called, well, sprite variables. But one of the things I'm going to do, because writing sprites is one of the really common activities in the game, not going to be so common in this game, but because it's something that happens so often, I'm actually going to define these variables in a special region of memory called HRAM, or high memory. It's 128 bytes, I think, of internal memory. And there's instructions that can access it faster than regular memory. And in sprite memory, I'm going to create a variable called shadow OAM head. With which okay. So the way that I'm going to be writing sprites is you have 40 different sprites across 160 bytes that you can use for drawing sprites. And I'm going to be following a very simple routine for drawing sprites. Anytime you ask the sprite system to draw a sprite, here in Sprites Draw, what it's going to do is it's just going to take up the next slot. It's going to start with a counter at shadow OAM head, and every time you call sprites begin frame, it's just going to set that head to 0. It's going to indicate that's going to draw to the first slot in OAM. And every time you draw sprites, it's just going to start working its way down the list of available OAM slots. So shadow OAM head is going to be that pointer to which OAM slot I should write to next for the next call to sprites draw. It's just going to start at 0 on every single frame. And then I'm also going to have a working variable, which is sprites draw count ds1. And this is a little counter variable that I'm going to be using inside sprites draw. Okay. So when I begin a frame, the first thing to do is set it to 0. Is set the little counter to 0 because we're going to be beginning a new frame. We're going to be starting to draw sprites from scratch. So cute. And there's the special instruction load H, which is a regular load instruction, except it's specific to high memory, and it's like it's a cycle faster. Yeah, so this is like 3 cycles. Whereas the regular N16 variant is 4 cycles. It saves a cycle. Working with high memory. So in my previous code, I've got this really big routine here for very intelligently erasing shadow OAM by setting the Y coordinate of every single object to 0. And that's all that you need to do to clear shadow OAM, because all that does is it just moves the sprites off screen. The top coordinate of the screen, as far as sprites are concerned, is actually 16. A Y value of 16 will align a sprite to the top of the screen. If you set it to 0, that'll actually set the sprite above screen. And that'll make it so the sprite doesn't draw. It sets it to 16 because there's an 8x16 mode for drawing sprites. And so if you have the 8x16 mode, making it so that a Y coordinate of 16 equals 0 on the screen makes it so that setting your sprite Y coordinates to 0 will make it so that no sprite will display regardless of whether you're at a mode of 8x8 or 8x16. And one of the reasons to move, and the reason that you want to set your sprite coordinates to 0 in order to erase them instead of like setting the tile index to a transparent tile is because the Game Boy also has a hardware limitation where you can only have 10 sprites visible on a row. If you try to put more than 10 sprites in a row, any sprite after the 10th will just not appear, which is why, and the NES has a similar limitation, which is why on the NES and on the Game Boy you get things like sprite flicker and sprites clipping, because you can only have 10 appearing on a row on Game Boy. I think the limit's 8 on NES. So I could go through and do some clever logic to iterate 40 times and just set the Y coordinate byte to 0 on every single one. I'm just going to do a really simple thing right now and just do a mem set to just set the entire memory block to 0. It's a lot slower than it needs to be, but I don't think this game's going to be very CPU intensive, so I can probably spare it. Plus, this does not execute in V blank, so it's not as time constrained. Shadowing and length is 160. That works, right? Yeah. Okay. So I just spent a whole lot of time explaining all about hiding sprites, but all I'm going to do is just set the entire memory region to 0. That's going to include the Y coordinate, and that'll be enough to hide it. Like setting the Y coordinate is all that I need to do. I don't need to set the X coordinate to 0 and the tile index to 0 and the attributes to 0, which is what's happening by doing memset. I only really need to be setting the Y coordinate to 0. And I could save time by doing that instead of erasing all of memory, but it takes less time to write this code. So this is what I'm going to do for now. Nothing's broken right now, right? Yeah, cool. Okay. All right, so the next thing that I'm interested in is sprites draw. I'm calling hero draw, right? Yep, sprites begin frame and then hero draw. And so to walk through this code a little bit, for the main loop, I halt until vertical blank starts. This detects when vertical blank starts, and the very first thing that I do is I call OAM DMA run, which copies the previous frame's shadow OAM to regular OAM. And then I update palettes, and then I begin regular gameplay code. I'll run input and then signal sprites. I'm going to begin drawing sprites to shadow OAM, which will be transferred over to regular OAM on the next frame. And then I call hero draw, which is going to draw the hero sprite to shadow OEM. Then we'll loop back to the main loop, halt again, wait for the next v blank, continue. Don't you have to no op after the halt? Oh, don't you have to no op after the halt? Yes, but I believe the RGBDS automatically inserts a no op after the halt for you. I don't think that because yeah, so it is a hardware bug. There is a hardware bug on the Game Boy that makes it so that the instruction after a halt isn't executed, and so what you need to do is put a no op after it. But I believe RGBDS as a just standard feature that's enabled by default is it'll automatically insert a no op for you after a halt, so you don't actually have to write the no op yourself. But let me check that real quick. I think there's a flag here. Yeah, halt without no op. Yeah, by default, RGB ASM inserts a no op instructions immediately after any halt instruction, but you can do a flag if for whatever reason you want to be taking care of that yourself. So, yep, totally fair question. I do not put a no op after the halt because the assembler puts it in for me. All right. All right, so this is going to call Sprites draw, so I just need to write this to shadow IM. And this is quite a bit of code. Oh boy, it's quite a bit of code. How am I doing on time? I'm an hour 20 minutes. I think I should still be able to get input in here and move the hero around. All right, so what am I going to be doing? Well, first let's load the type. Huh, that's cute. Ah, yeah, okay. Yeah, so I'm looking at the code that I previously wrote. So one of the things about it was the previous game was large enough that I needed banking. So one of the things that was defined previously was the bank of sprite definitions. This isn't going to use banking at all, so that stuff doesn't exist. I also had some debug code that I'm not going to be using here. So HL is the address of the sprite definition right now, and the very first byte of it is the type, either 2x2 or 1x1. So first, load sprite def type. And then when I do that, it's not going to, yeah, it doesn't say any flags. Okay. And I'm going to write a to-do and then move on with my life. To-do, handle 1x1 sprites. Right now, I'm just going to hard code. I'm going to just I load that, I load the type, and then I advance HL to struct here. And right now it's just going to be hard coded to only support the 2x2 sprites. I'm going to change it. I'm going to add support for 1x1 sprites later. So let's see here. Let's have a block here to draw 2x2 sprites. Yeah, this is just going to be really hard coded. I don't think I'm even going to have a loop in here. Because the arrangement is going to be hard coded. Yeah, it'll be easier if I don't do the loop. So all right, so I have HL as my source data. I need to have the destination data, which is going to be shadow OAM, offset by shadow OAM head. In fact, since I don't have loops, This isn't actually used for anything, so I'm not actually going to need it in this game. So I guess I'm just going to be putting shadow OAM into BC then? Okay, but I need to offset by shadow OAM head. I really want to have that in DE, but I guess I'm just going to use it in BC. Okay, so let's set BC to the address of shadow OAM at shadow OAM head. Okay. And then I need to shift it left twice in order to effectively multiply the. All right, so shadow OAM head. The byte. Okay, I don't need to shift it. Oh, that's nice. Okay. Okay, so at first I was thinking of it as an index, and so I would need to multiply it by 4 in order to make it the offset, the byte offset. But if I'm just going to be storing the byte index, I'm not going to need to shift it left, and I think this is actually going to be totally the correct thing to do. Yeah, this is definitely going to be the right thing to do. Okay, so now I have A as the byte offset into shadow OAM head. Load BC memory shadow OAM. And then the thing that's cool about shadow OAM is I have a guarantee that the low bytes here are going to be 0, 0. It has to be aligned to, I think it's a 250, yeah, it's a 256 byte boundary. This memory region is 160 bytes in length. I know that oh, this is gonna be even easier than I thought. So I know that like initially the low byte of mem shadow OAM has to be 0, basically, which means I can actually just take this A and load it right into C. In fact, I think the appropriate thing to do here is to ignore the load A instructions, just load directly into C, and then load into B the high byte of mem shadow OAM. That's invalid. That is actually invalid because, oh, right. Okay, no, this is, because you can't, because there's no N16 for that. Okay. So I'm going to load the offset into A and then put it into the low byte of BC and then set B, the high byte of BC to the high byte of mem shadow OAM. I don't actually have to do an addition because I know that C is 0 and 0 plus whatever this is going to be whatever that is. So I can just load it. All right, so all right, so I have BC there. Okay, so I now have my destination pointer. I have my source pointer. And I have my X and Y in D&D. So, next. So I'm going to do top left, I think, top left, top right, bottom left, bottom right, top left, top right, bottom left, bottom right. All right. Let's see here. OAM. Okay, so byte 0 is the Y position. So right now that's just going to be can I load E to BC? I cannot. It's gonna have to be A R. Load into R. Can I load in? Load in to B. It's gonna have to be A. Yeah, okay, so load A E, which is my Y coordinate. Load that into BC. Increment BC. And then the X coordinate, BD loading. I think it's gonna be better if I use HL for this instead of BC. We'll get to that in a bit though. Okay, so then the next byte is the tile index, which I think is, yeah, so then it's tile index and then it's attributes. Okay, so next is copying 2 bytes. So load A, HLI, load BC, A, increment BC, and then repeat. This should actually get me my top left sprite here. Yeah, kinda. Oh, I know why that's showing up in the wrong coordinate. Okay, cool. All right. Yeah, I think I want to swap where I'm using HL and BC because the thing is there's the HL increment instructions. And I'd like to use them in 4 operations instead of only 2. So I think I want to swap around HL and BC. So I'm going to instead set HL equals, or so I'm going to set BC equals the address of sprite objects. H into B, L into C. Okay, and then HL will equal shadow and blah 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 blah. HL, so that way I can do HLI and delete that. HLI, then delete that. And it's still going to be increment BC. Yeah. All right, there. And so that should cut out. How big is it? Is increment? Yeah, that's going to save 2 cycles per sprite, or 4 cycles per sprite. Okay, so it's still the same effect there. All right, it looks like I don't have the Game Boy palettes loading quite yet how I want them to be. DMG object palettes. Yeah, I'm not using that with anything yet. Should be reading that from memory. Okay. All right, then let's load up. How big are these? These are just 8 bits. Yeah, yeah. I already had the palettes defined. I just wasn't loading them yet. So that should fix the way this sprite looks. Yes. Yeah. All right. Yeah, I'm gonna select second palette soon. And by soon, I mean right now. Let's just do it right now. I want the sprite to look right. It's gonna be bit, what is it, bit 4? 0, 1, 2, 3, 4. Yeah, it's gonna be 1, 0, right? Yeah. Why did that not do what I wanted it to? Object pal 0, object pal 1. Oh, because I didn't. Okay. I think 1 is black, so I think. All right, what have we got? Is it 1 1 is black or is it 0 0 is black? I think it's 1 1 is black. I think it's backwards from what's intuitive. So let's try 0 0 0 1 and see what happens when I do that. There we go. All right, that looks how I want it to. All right. Now, I think the hero is supposed to go here. So why isn't he? No, the hero's supposed to go like right here. Where is the hero? All right. 9. Here's 0, 1, 2, 3, 4, 5, and then 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. All right, so there's some camera panning, then there's also the weirdness about where the top left is. Sprites, but I guess I just add 8 to it. That's going to put it in the right spot. That feels all kinds of wrong. No, that's actually totally right. Yeah. Okay. So, on the Game Boy, setting like a Y coordinate to 0 will actually set it 16 pixels too high because you need to be able to hide in that way. So saying a Y of 16 will actually set a sprite to the top. So that would suggest that the Y coordinate should be 16 pixels lower away from where it is in its logical space. But I've also scrolled the map up 8 pixels in order to clip off parts of the map so I could have a larger playable map field. And so that actually means, so that's subtracting 8 pixels from those 16 pixels, which means I only need to adjust 8 pixels down in order to get the right size. And then the X coordinate is in the right thing because the X offset is 8 from the left of the screen instead of 16. So it's probably a rambling rant that didn't actually make any sense, but it makes sense to me in my head. So. All right, so the next thing that I'm thinking here, do I want my gameplay logic that's asking it? I think I'm going to go ahead and allow my sprite system to know the fact that my maps are offset by 8 pixels. So I'm going to put in, so I'm going to have the sprites draw routine contain the X and Y in gameplay pixels space, and it's going to make the appropriate offset to screen space pixels instead of me needing my game objects to make that adjustment. So isn't things making sense in our own heads what we're really after when we talk about things making sense? Also made perfect sense to me. Awesome. Glad to hear it. All right, so characters displayed at the correct position there. We just need to get the other 3 objects displayed. Well, I'm glad what I said made sense. All right. And then that will be drawing the hero. So now, okay, so the top right, so I just need to shift X plus equals 8. Oh, no. Okay, here, all right, so here's what I'm going to do. That should be enough to get the top right coordinate in place. Yeah, that was easy. All right, and then the bottom left, Is this with the y coordinate added by 8, and then the bottom, let's go ahead and see it now. All right, and then the bottom right, so that's bottom left. All right, and then the bottom right is both the x and y plus 8. And that should draw the whole hero. There he is. Look at him. Cool. There he is there. There he is there. We are successfully drawing the hero. I kind of want to... So one of the things that you can do to add a little bit of an added sense of perspective or depth is to like take your objects and shift them up a couple of pixels so that they overlap the background tile above them a little bit. Like, let me just show here. Can I just do that? So that's gonna be, yeah. See, it just slides them up a little bit. I can be even more dramatic. Slide them up 4 pixels. And there he kind of looks like he's standing in the environment and overlapping the gem or the square above him. I might go for that later, but don't need that anymore. In fact, I'll just comment that out. I'll put a pin in that, that's something I could do later. For now, just to simplify logic, I'm just going to have him in a more simple logical position. I'm not going to try to do a cute graphical effect to shift him up a little bit. Instead, I'm just going to leave him right there and just implement my movement code now. So we now have a sprite system. We have a drawn hero sprite, and we now have a sprite system. So I think I can actually check that off on the agenda. So next, all right, so where am I at right now? An hour, 40 minutes. I'm going to go ahead and go a little bit longer than 2 hours for the sake of getting this done because I really want to get movement. I really want to have an interactive game on this, the 22nd of August, with only a bit over a month left in the Game Boy competition. I want to actually have something that I can push buttons and move the character around on. So, load tile set, video update, sprites in it, sprites begin frame, sprites draw. I think I'm done looking at this old assembly code. Yeah. Oh no. One last thing I have to do. I'm gonna do it right here. All right, this is gonna be a little weird. I'm gonna look like I do something a little bit redundant. It's just going to save me from writing a bug once I implement 1x1 sprite mode. 16. I'm gonna offset shadow OEM head by 16 so that if I write a second sprite, shadow OEM head is that the correct thing. You're supposed, I have to increment shadow OEM head after every sprite draw based off of how many sprites I wrote to shadow OEM. So I just need to do that. And so the thing that I'm going to do that's going to look a little redundant is at this point, A already contains shadow OEM head, but I'm just going to load it again. Let me see. I'm just going to load it again because there's probably going to be a branch after this at some point in the future, and A might not contain it anymore. So I'm just going to load it again just to make sure I'm safe, even once I add the branching later. Add 16 and then load H, shadow IM head. This should not break anything. Yeah. Okay. Yeah, so again, it looks redundant right now because A already contains shadow IM head, but because later I want to add support for handling 1x1 sprites, there's going to have to be a branch here somewhere. The branch might be here later, and I might put something into A in order to do that later. So I just gonna load it again inside this loop just to be safe. But if I ship it this way, somebody's gonna look at the code again and be like, why? And that'll be fine. But that's it for the sprites.asm for now. So I'm gonna close that. All right, let's grab my Game Boy Advance C code. I turned my Game Boy Advance off, right? Yeah. So with the hero, we have hero draw, hero spawn. So I want, yeah. So there's going to be a routine called hero read input. Takes no arguments, returns nothing. It's going to do exactly what I just typed. It's going to be a public routine. All right, so in main.asm, so input update is the hardware routine to query the joypad register. Hero read input is going to be the game time hero routine to do something useful with those controls. Map select. I think now is the time to. I was gonna say I think now is the time to get rid of map select, because the thing is, I was using the D-pad. Where's map select? Oh, here it is. Because I'm using the D-pad to let me load the different maps. Here I can use left and right to do that, but now is the time that I actually need to have the D-pad available for moving the hero. But I think what I'm going to do is instead, I'm going to remap those controls from left and right. I'm going to instead change it to select and start, because I don't need to use those yet. So let's do F input select. And start. In fact, I don't think I'll be able to leave it the same here until I'm like way deep in game development and actually have the menu with the level select screen open. I think I can just leave these as select and start for now. So start, select. All right, and the D-pad is now open, so I can let the hero work with the D-pad. All right. So there's going to be hero read input, and then there's going to be hero update. Yeah. This is going to be split into more routines later, but I'll explain in just a minute why I'm writing like something I want to do with the hero code. So. All right. So let's go to this for a little bit so you can see the little playdate animation right now. So this is a game where you can move the hero a square at a time and push blocks around. There's little animations as it moves from square to square. So what I'm going to be doing is I'm going to be splitting up the process of updating a hero into updating a hero for a frame across multiple routines. And the reason for that is that some of the routines are going to have the hero writing the hero's intention for that frame to a temporary variable, and then it'll return, and then I will let other systems run in order to let them query what the hero wants to do in order for them to decide whether to allow it to happen or prevent it from happening. So for example, when the hero wants to move, I will have the hero record an intention that says, I want to move to the right. And then that function will return. It won't actually make the hero start moving to the right. Then what I'll do is the game will ask the map, hey, go ahead and do a bit of an update responding to the hero input. The hero wants to move to the right. You get to decide whether or not the hero gets to proceed with that. And the map will ask, hey, is there a solid tile to the right? And if there is, then the map will take that hero intention and overwrite it. And it'll say, instead of moving to the right, you should instead not move to the right and you should play bump sound. And then the gems that you see there are going to be a little bit similar. They'll be allowed to process the idea that the hero wants to move to the right, and they'll be like, is there a gem to the right? Well, can the gem move? Because if there's two gems of opposing types next to each other, they can't move any further and it'll block the hero. If it can move, then the gem will also move to the right. Otherwise, it'll block the hero. And so the idea is I'm going to be splitting up the hero into the hero update into multiple routines so that in between processing parts of the hero movement update, I can run other code that can change what the hero is going to do. To start with right now, I'm going to be implementing a function called hero read input, which just reads the input and decides what the hero is going to eventually want to do. And then for now, I'm creating a routine called hero update that's just going to move the hero. For right now, nothing gets to interfere with the hero moving. It's just going to move the hero. What hero read input is going to do is on any given frame, it's going to read the D-pad. And based off of if the D-pad was pressed in this frame, it's going to record the fact that it pressed that input to a memory variable. And in hero update, if the hero is standing still, it'll look at what the last D-pad direction that was pressed was, and it will move accordingly. If the hero is actively, and then it'll erase the previously input direction. If the hero is actively moving, it'll just completely ignore whatever the last D-pad input was. And so what's going on here is I'm going to be doing what's called input buffering. The idea is you press down and the hero is going to move down 16 pixels. If while the hero is moving down, you press left, he's not going to immediately move left. He's going to finish moving down, but once he reaches the bottom, then it's going to say, oh, I previously pushed left. Now I'm going to try to move left. And that's going to make it so that you can like rapidly mash D-pad buttons and the hero is going to respond to it without eating your inputs. If you didn't buffer the inputs and you press left while the hero is moving down, the hero would continue moving down and then just stop. So hero read input is about recognizing on any given frame when we've pressed a D-pad, we want to buffer that input. And then hero update for now is just going to, when the hero is standing still, consume that pressed input in order to send him off in a direction. If he's moving, then it's not going to touch the buffered input. So on the Game Boy Advance version of the game, I have 32-bit signed integers, and I can just store whatever I want in them. It's going to be a little bit different how I'm going to handle it on the regular Game Boy, but I still need a state. So I do need a state machine for the hero's state. There's going to be an idle state and there's going to be a moving state. So what's the syntax for defining those? Equal. Okay. Kind of. Did I have the standard here of doing k underscore? I want to do k underscore. Do f underscore and bit underscore. I'm going to define k underscore because it's my code and I can do that if I want. Hey, I do have some k underscores. Okay, so there's going to be a hero variable called hero state. Not a very descriptive comment, but all right. And then when the hero spawns, we're going to start him with a state of idle. Okay. Technically, since k hero state idle is 0, I could do x or a, which would, I think that saves a cycle, is it? That's one cycle. That's two cycles. Yeah, it would save a cycle if I did x or a, but I want to be using this named variable just to make it super clear what's going on. Okay. Da, 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 da. I don't know what I'm doing. I'm making things up as I go. These hero direction constants eventually are going to be in an include file, I think, because they're what I'm going to write to a global intended hero action variable thing, probably, and other routines are going to need to be able to respond to it, so they need to know. So they're going to need to know it, but I don't need that for this session. This session, the hero is the only one who cares about where he's moving. All right. So we need a variable to hold the buffer direction. All right, we need to be able to have nothing held for when we haven't buffered any inputs. In fact, I could probably actually make these equal to the Game Boy joypad. Yeah, you're all going away. Okay. No, I'm keeping them. Okay, so the thing that went through my mind very quietly just then was I was thinking, I've got constants defined for the Game Boy. I have not been showing my code for how long have I not been showing my code? Let's go back to my code. Okay. I've had it on my camera view for like, I don't know, the past 10 minutes or something. Let's go back to the code. How long have I been showing that? I don't know. Okay. Sorry. So the thing that I was thinking with these constants was that I could have I've got constants defined for the gamepad D-pad buttons. And the idea was maybe I could just like store those directly in the buffered input variable that I have. And then I was starting to think, oh, so then what I could do is I could look at the buttons that were pressed this frame, mask out, like select start B and A, and see if the remaining value is not equal to 0. And if so, I could just write that into the buffer. I was like, oh man, that would save so many instructions and it'd be so clever. The thing is, I only want to store a single direction at a time. I only want to store a single direction in the input buffer. And so even if I was reading it and using those constants, I'd still have to check the bits one at a time. I got a comment. I was just doing something else and listening to your soothing voice, so I didn't even see it. Awesome. So I think I'm still going to go ahead and keep these separate definitions. I know I go to D-pad, but I mean, it's fine. Okay, hero direction, none, up, right, left, down. Okay. All right, hero buffer direction. All right. Okay, so when the hero spawns, the buffered direction is going to be none. Buffered direction. And again, direction none is equal to 0. I could just do X or A, but I'm not gonna, just for clarity's sake. All right. On read input, joypad press this, input just pressed. Okay. So in here, read input, I'm gonna read in the buttons that were just barely pressed this frame. So just pressed contains bit set only if the buttons are pressed in this frame. It's not the same as like the current state of the gamepad, which is input pressed. Input just pressed only lights up those bits on the single frame where you first start pressing a given button. So this is like a key down event. All right. Why did I do dot? Bit, bit input. Oh, right. I need to include input.inc / input.inc. Might need to refill my water before this is done. I think I'm close to done, but bit input down A. To relative not 0. Okay. In return, I guess. All right. Okay. So the idea is we're loading the just pressed buttons into A. We're checking against the down button. If the down button was pressed, that will set the 0 flag, right? No, 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 no. It's just the opposite. The 0 flag is set if the bit is 0. Okay, 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 okay. So it's setting the 0 flag to the status of that bit. So if it is 0, then we're going to go to end down. If it is 0, then we are not pressing down. We're going to move on to the end of this block. If it is 0, then we're going to load the constant k hero direction down into A, and then load that into the buffer direction, and then return. This instruction destroys the value of A, making it no longer hold input just press, but we will return if that happens. So in here, we can just change to up. This should be fine. Right and left. All right, and technically in this last one, instead of jumping to end left, we could just return if it's 0, but I'm just going to leave it as it is right now, just so that all these things are the same. All right, I should be able to use the debugger and log out the value of it and make sure that I'm to log out the value of the press buffer and make sure that I'm recording it correctly. So let's see here, print. Oh, nice. It's got tab completion. What's the name of the variable? Hero buffer direction. So it's 0. All right. Press up. Oops. Log it out now, and it's 1. Press down. Log it out, and it's 4. Press right. Log it out, and it's 2. Press left. So by process of elimination, this should be 3. 3. Okay. So it's up, right, left, down. See what I declared these? Up, right, left, down. Cool. Excellent. All right. So I'm successfully buffering the input. Oh. So that's that routine. So it's just one routine is left. Hero update. Except I'm probably going to split into 2 routines, 2 subroutines. Almost done. We're almost done here. All right, so I'm going to create 2 private routines. I'm going to create I'm going to create 2 private routines. I'm just going to do something cute with how I call them. All right. Hero update moving. So a routine updates the hero in the moving state. I'm going to create a second routine, second private routine called hero update idle. It's the hero in the idle state. All right. Now in hero update, what I'm going to do, so in hero update, intuitively what I do is I'm going to read the value of the state variable. And if he's in the moving state, I'm going to call the moving state handler. And if he's in the idle state, I will call the idle state handler. Pretty straightforward. But the thing that I'm going to do is I'm going to particularly do the moving state first and the idle state second. And it's not going to be the like C equivalent of an if statement followed by an else if. Instead, it's going to be the equivalent of two completely separate if statements, because the moving state can transition to the idle state. And if that happens, I want in the exact same frame to process the input and possibly transition into the moving state that very same frame. So it's the order the state transition is deliberate, and the fact that I'm going to be checking the state before the idle check as well is also deliberate, because the moving state might trigger the idle state, and I want to be able to process both states in one frame. Okay. Hero state. So we're going to compare it to k state idle. And so we're going to call z hero update. Oh, no, I want to check moving. All right. If hero state is equal to moving, call moving update handler. If hero state is equal to idle, call idle update handler. Okay, now let me check my condition flags again. It'll be 0, and this time if it is 0, the affirmative thing I want to do is call the function, so z is correct. Okay. I'll be right back. I'm going to get a little bit more water. All right, I'm back. All right. So I need some temporary variables. I'm going to need step x, and step y are going to be the variables I'm going to add to hero x and hero y every frame when they're moving. The number of pixels to change in the x and y direction per frame. Target x and target y is the destination coordinate in pixel space of the hero, and that's it. That's all the temporary variables I need. added to hero X per frame when moving. Value added to hero Y per frame when moving. X target X coordinate when moving and target Y coordinate when moving. All right, moving update is actually very, very simple. If we are currently moving, it's very simple, but it's not as simple as C. Step X. Can I add to an N16? No. Can I load this from an N16? No. Okay. Be that way. A lot more instructions than I want. Okay. We're going to load our offset into A, then we're going to temporarily move it to B. I feel like I should be able to like do this, load HL hero X, and then add that. I feel like that should be equivalent. Is that faster? It's one fewer instruction. Let's see here. Load A from an N16 is 4 cycles. So that's 4 cycles, and that's 4 cycles, and that's also going to be 4 cycles, right? Yeah. All right, and then load BA is just a 1 cycle, right? And then add B, is that 1 cycle? Yeah, it's 1 cycle. Okay. So this whole block is 14, 12, 13, 14, so this is 14 cycles. All right, this other option, this is 4, and then load HL N16 is 3. All right, and then add HL is 2. And then load HL with the value in A is also 2. Is that faster? 4, 5, 6, 7, 8, 9, 10, 11. It's faster. All right, does this do what I want it to do? Load the step X into A and then load into HL the hero X coordinate, add hero step X to hero X, and then load that into HL. Yeah, all right. Cool. Optimizing on the fly. Hero X plus equals hero step X. And then hero Y plus equals hero step Y. All right. Just as a heads up, one of the things we're going to be taking advantage of here is the fact that for the use case that we're doing, the math of signed numbers and unsigned numbers is identical. So what we're going to be doing is hero step X and hero step Y could be positive. I think it's going to be 2. Yeah, 2 pixels per frame. So it could be positive 2 or negative 2. And negative 2, I think, is 254. And the fact is when you're adding them to a byte, it produces the same result. So we're going to be doing signed math just using U8s. That's going to be cool. All right. We move hero X according to the step offset, and then if the hero X equals target X and if hero Y equals target Y, then we transition to the idle state. So if we've reached our destination, we transition to the idle state. So what we're going to do is we're going to declare a label here called reached destination. And we're going to load the state idle, and then we're going to load that into hero state. Hero state idle, and then we return. Okay. So is hero X equal to hero target X. I'm just like so disappointed by the instruction set on such a regular basis. Okay, if they're not equal, then we just want to return 0. Then we just want to return. In fact, we don't actually need the reach destination block here. What? Okay. So if those two values are equal, then when we compare them, they're going to be 0. If they're 0, we should move forward. If they're not 0, we should bail out, because the last thing that we want to do here is transition to idle state. So. Okay. One routine left to write, and then we should be done. That is updating with idle. What do you want? This is a deck from 1987. Yeah. This particular CPU is from 1983, isn't it? The SM83. But yeah. I mean, you're totally right. It is a very early CPU. There's going to be a lot of instructions I wish I had that I didn't. All right. Hero update idle. Okay, so if we're in the idle state, what we want to do is we want to see the buffered input. If the buffered input is nothing, then we return. Otherwise, we're going to configure target X, target Y, step X, and step Y. Reset the buffered input, transition to the moving state. Okay, so load a buffer, hero buffer direction, compare to 0. Oh, you could do, instead of compare to 0, I could do or 0. Right? That is faster, right? That's 2 cycles. That's 1 cycle. So I could compare it to itself. No. Compare. I don't want to think about this anymore. Compare hero direction none. Then return 0. If there's no buffered input, just return. Okay, so compare it to hero direction none. And if it's 0, we want to return. Okay. We're going transition to moving state. Node A, K state hero moving, load hero state A. Oh man, it's so much code that I'm writing without testing here. There's almost definitely going to be a bug, but we'll see when we start running it. Transition to moving state. And I think what I'm going to do is I'm going to start by setting target X, target Y, step X, and step Y all to 0. And then I'm going to branch on what direction we've held down. Well, it's a modified version of the extended model of the SM8313. So actually an SM8315, if I recall, that Sharp had just freshly cooked up. So you can use more memory in 1987. Interesting. Just freshly cooked up so you can use more memory in 1987. Okay, I thought that like the Game Boy community had been referring to it as the SM83 because it was a Sharp CPU that came from 1983. Does the term SM83, is that just a shortening of SM8315 then? Instead of just like a reference to the year that the processor came out with? The original could only access 8K or something. Interesting. Transition to moving state. Reset, target, and step bars. Sharp model 83. Not sure what it means. Huh. Yeah, I'd figured 83 was a reference to the year, but I guess I don't actually know if that's true. The important thing is that the Game Boy community decided that it is not a Z80. That's like it's derived from or based on, but not actually a Z80. Despite the fact that it's popularly referred to as a Z80 in much of the world. And my RGBDS extension for Visual Studio Code is called RGBDS Z80. It's a bit of a misnomer. All right, reset target and step bars. So we're going to load a 0. We're going to XOR A, and then load it to hero step X, hero step Y, hero target X. The actual chip with the APU and LCD driver and stuff is an LR35902. Interesting. XOR A, hero step X, hero step Y, hero target X, hero target Y. Okay, now we're going to branch on what the hero direction was. So we're going to load to save me a cycle or two. How long does it take to load this from scratch? Load A, N16. That's 4 cycles. Yeah, it's definitely going to save me a cycle to do this. Load buffered direction back into accumulator. All right, and then also I need to clear out the buffer direction. And technically, you know, I made the constant I made the buffer direction none equal to 0, so I could technically just reuse A from up here, but I'm gonna again load the constant into A just for code clarity purposes. Okay. SM83 equals single chip 8-bit CMOS microcomputer for voltage synthesizer and on-screen display controller. I mean, what? What else was the chip used for? I mean, I know it was used for Game Boy. Was it custom for Game Boy? I think I heard something about like Nintendo adding things to the chip or customizing it. Was the chip specific to the Game Boy, or was that particular chip used in other things? Load buffer direction back into the accumulator. All right. So next we're going to compare it to... a hero direction. So we're going to compare jump relative to its yeah. This is the sort of logic I was doing before. I don't actually need the colon, do I? Jump relative, not Z, and down. All right, so step, if we're pressing down, step is going to be 2. And then the target Y hero Y, add 16, target Y, A. Okay. So press down. If we're not pressing down, then we skip to N down. Otherwise, we load 2 into A and then load that into hero step Y. Then we load hero Y into A, add 16 to it, and then store that in the target Y. And then return. Okay, let's do up next. Yeah, let's do up next. The SM83 series, 8311, 8313, 8314, and 8315 found a lot of use in other things too. Game Boys were definitely the most popular by far, though. I can believe that. All right, K hero. I mean, not just because the Game Boy sold so many units, but it was like the Game Boy and Game Boy Pocket and the Game Boy Color all had literally the exact same chip, right? And then the Game Boy Advance continued to use the exact same chip for the sound processing, right? And I guess for backwards compat mode. Like that chip stuck around. Didn't that chip stick around until it was either the Game Boy Micro or the Nintendo DS, right? It's like at one of those stages they started switching to they needed to be able to support the Game Boy's hardware or the Game Boy's audio registers, and so I think the Z80 was used to control something with that. I don't know, but it's like once they got to the Micro or the DS, they start either emulating the sound controller or just handling it differently or something like that. Game Boy Advance sounds different, very different. Well, when you're using Game Boy Advance native sound, yeah, it's got those 2 extra sound channels, but it's also able to make use of the Game Boy's sound registers for like square waves and stuff, right? Does it use the Z80 for that, or the SM83 for that, Or does it completely control the hardware itself when you're in Game Boy Advance mode? Does it use this SM83 at all for sound in Game Boy Advance mode? SM83 doesn't include the APU or the LCD drivers. Okay. Nope. Okay. All right. Up, up. All right. So, will this work? Seems to work. -2. Well, okay. I don't think that my extension is handling -2 correctly, but -2 as a U8 should be, I think, 254, and this should work correctly. We'll find out very quickly. All right. Then let's do right and left, and that should finish this. That should finish all the code that I want to write today, unless there's bugs, which there probably is. So this is going to go in hero step X, hero X, hero target X. Hero step X, hero X. Okay. Unless I'm forgetting something or there's a bug, that should be it. And I should actually be able to move around now. Let's see. Right? Whee! Ha ha ha! He's not stopping. Okay. Up. Okay. He's going up forever. Down. And he's going down forever. All right. And left. He's going left forever. Okay. It's not correct, but at least he's consistent. Okay. So why is this happening? Why doesn't he stop? Okay. So he starts in hero state idle. We call heroes. So I think the problem is that he's never transitioning to the idle state. Why is he not transitioning to the idle state? Oh, no. I think I know what it is. I think I know what it is. Okay, so the problem was that I'm setting the target X and target Y to 0. I should actually be setting the target X and target Y to whatever the existing coordinate is. This is probably a dumb idea, but I kind of feel like building a new retro computer in the style of the IBM 5150 with an SM8315 now. So not so much a chip that old to me, but mucking around with like the Game Boy Advance and the Playdate now, especially the Playdate, it's been really interesting exploring like these older computers with simpler memory spaces and things like that. It's really fun to play around with. And yeah, you know, it kind of makes you want to experiment with it and things like that. So these target vars need to be set to the current position. So load a hero X, hero Y. If that's the only bug that existed here, I'm gonna be so happy. Ooh, 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 ooh. And the buffered input works correctly. It works. Oh. All right, I should be able to. Yay! Yay! I think it works. I think I'm done. I think I'm done. 2 hours and 40 minutes. This is my longest stream ever, but I think I did it. Hooray! Oh, oh man. What it'll look like in Game Boy Color mode. I'm gonna predict that in Game Boy Color mode, the hero sprite is just going to be pure black because I don't think I'm loading any object palettes. And I'm not setting the attribute for it. Which should just load object. Oh no, it's going to be something garbled because the sprite palettes are random when Game Boy Color boots. So he looks different every time I reboot. Yeah, cool. Going back to being limited to only having 32K of ROM and 1 kilobyte of RAM, though, oof. One of the funny things about Game Boy programming that I've found, you are super starved for CPU time. The CPU time I always find to be a giant pain, which is a big part of why I'm like writing assembly right now and trying to figure out how to be comfortable writing assembly. You're just always so desperate for CPU time. ROM, especially given the fact that ROM, especially given the fact that in modern homebrew development, you really don't have any practical limits to ROM size. Like back in the day, you'd have economic constraints on ROM size, where the larger the ROM chip, the more expensive it is to manufacture the cartridge, and that doesn't apply anymore to homebrew. So, like in modern Game Boy homebrew, you can really make your game as large as you want. It doesn't really matter, but you do have to be aware of like banking. You have to write code to support banking, but it's not really that you're really limited by ROM size. You just have to handle banking. RAM, for whatever reason, um, on Game Boy, I haven't felt it as starved by at all in my games. They tend to be simple games, but my last game, Bubble Factory, used something like 40 bytes of RAM. A lot more video memory, but just regular RAM only about 40 bytes. And so on Game Boy, for whatever reason, for the games I've been doing for right now, RAM has been the resource that I feel least constrained by. It's just not been a challenge to me at all. That's a big part of that is because of the types of games I have. So if I only had 1 kilobyte of RAM for the kinds of games that I've been doing, I'd be kind of like, oh yeah, that's kind of fine. But that's for the kind of games that I've been doing. Overclock it at 5 volts, safe to run at 8 megahertz in M cycles. Is M cycles the machine cycles like the Game Boy is currently at 4 megahertz and Game Boy Color it goes up to 8 kilobytes? A kilobyte of RAM includes any VRAM. Okay, yeah, that would suck. That would suck. At least it's not the Atari though, right? That's 128 bytes including the stack. Although that might have separate VRAM. I don't know. Does the Atari have VRAM, or were you having to? I don't know. The Atari, it's like I read about the Atari a little bit, and that sounded really painful, and I didn't want to write that. On the Game Boy with 8 kilobytes of RAM, excluding video memory, in my experience, that's felt like really spacious. So, I should be able to wrap around to the other side, and it shouldn't make any difference. All right. Cool. All right. I am really happy with this. This was a good stream. Got some good progress. Let's load this. You'd have to put a graphics adapter on the ROM bus and communicate with it through unverified writes. Was that the Atari that you're talking about there? All right, so that should take care of all that. I want to put this on my Game Boy right now. I'm gonna load I'm gonna load this ROM onto my Game Boy. Nah, still the SM83. Ah, okay. Wonder why I'm draining battery while doing this. I have it plugged into power. Maybe it's just that the external monitor that I have plugged into this computer draws so much energy that it's just has to draw from the battery. I don't know. Let's see here. Here's the SD card. ROM folder. Homebrew directory. Drag the game in there. Eject the SD card. Load into the Game Boy. All right, let's switch to the main camera feed. Same boy is very accurate, but if for some reason this doesn't work on real hardware, that's going to be annoying. It works, yay! All right, let's show this to you. All right, here it is. Yay! All right. That was a good stream. Let's switch back here real quick just for the satisfaction of checking off the last thing. D-pad movement is done. All right. So, flashcards are hard. Yeah, back in the day, you probably have had to. Yeah, so I'm using an EverDrive. Back in the day, you had to have, I don't know, something else, some dedicated hardware. Um, all right. So what did we do this stream? We drew the hero sprite. We got a sprite system implemented and started showing the hero on screen. The days when you had to mess with PROMs and sockets plus programmers was awful. Yeah. And we were able to use the D-pad to move the hero around. So next session, we're going to start implementing. So next session, we're going to do collision against terrain. And I think it's also going to be. No, that's not what we're going to do. I think, well, we might do collision against terrain. The big thing that we're going to do next session, I think, is going to be what I want to do, especially now that I've drawn the hero, is right now I've got maps defined as just hand-coded assembly right now with literal numbers implemented, which works with doing a couple of test levels, but to actually design the levels and port the levels from the other versions of my game to this, I want to use the tiled map editor. So next session, I think we're going to set up a tile set in the tiled open source map editor. And we're going to start defining tiles in there, and we're going to write a shell script that the make file will execute, which will convert from those tiled map files to this format. And that will let me edit my levels in a much more ergonomic way than hand typing the levels. And then I'm going to add in the solid map, or I guess I'm not going to define it as a separate map. I'm going to add in the basic collision system against terrain in order to make it so the hero can't bump into walls, so the hero can't walk over the walls. That's going to be the plan. So, thank you very much for watching. Thank you very much for chatting. Most of my streams, I don't have anybody chatting. I actually really prefer it when there's people to talk with. So thank you very much for tuning in, and I will see you next time.